Good morning, everyone. Welcome to the Pico-Seminar series, which is part of the Pico Electrodynamics Theory Network here at Purdue, where we are trying to bring theorists across working in very diverse field, including the topological electrodynamics, topological photonics, and the density functional theory and many body systems. So the idea of this network is to increase the collaboration to look into the atomistic picoscale effects inside the material, both light matter interaction and also the electronic effects. And we had several eminent people gave the seminar series, which is available in YouTube. And today we have with us, we have another expert in this field, Stephan Haas from University of Southern California. Now, Professor Zubin Jacob will introduce the speaker.
Great. Thank you so much, Satvik. So it's a real pleasure for us to have as our speaker today, Professor Stephan Haas from University of Southern California. So he will be talking to us about quantum many-body systems and topological edge plasmons in them. So he is a condensed matter theorist with very broad research interests, spanning all the way from quantum information theory and quantum magnetism to unconventional superconductivity. So they have also been, his research group has also been looking at numerical techniques such as quantum Monte Carlo to study phase diagrams, as well as excitation spectra. And he received his PhD from Florida State and spent some time as a postdoc at the Swiss Federal Institute of Technology. So we are very happy to have him here. And we are looking forward to working closely in the future as well on many of these topics. So without any further delay, Stephan, looking forward to hearing from you.
Okay, thanks for having me, and I'll try to keep it brief. So edge me along if my talk gets too lengthy. So yeah, so I'm gonna hold on. There you go. So quickly wanted to acknowledge collaborators I've been working with. Most of them have graduated by now, and most of this work was done by Jihao and Jiang, who's in the left upper corner, including some postdocs and colleagues. Okay, so let me quickly just sort of remind you of what I think of when I think of topological states. It's actually a mathematical concept, if you wish. That's not quantum. It is basically the idea that you have structures that can be characterized by something that's called a genus. And one way to visualize that is just to think about structures that have holes, and you can basically count the number of those holes in the structures. And we call these structures topologically equivalent even if you deform them, the number of holes stays constant. In contrast, if we actually have some sort of increase or decrease of the number of holes in a structure like here, then we're talking about a topological phase transition from one topological sector to another one. Now, how does this apply to physics? Well, there are quantum states that are topological in nature, and I'm going to talk about these mostly in 1 and 2 dimensions. There are actually physical systems that support such states, and for example, there's something called the chiral zigzag chain, and this is rather small, but it basically looks like a molecule, a one-dimensional molecule, on which the electronic states form some topologically non-trivial state. And even better known, I think, 2D structures such as the honeycomb lattice that support edge states along the sides of these open-ended 2-dimensional structures. And the states themselves is what is our focus. So they are, for example, valence bond product states, like indicated here, where you form some sort of bonding combinations along neighbors, or something like quantum Hall edge states, where you have states propagating at the edges, whereas there's nothing propagating in the bulk. All right. So what are the characteristics of topological quantum states, and why are people interested in them? Well, they are spatially isolated, so they live usually on the periphery of systems. If you don't have periodic boundary conditions but open boundary conditions, they will be on the edges. They're energetically isolated. So that means if you have electronic states in a metal, they usually form bands. However, topological insulators, they're actually insulators and only have a conduction in the topological states that live on the edge. So that's basically in the bulk the insulators. On the edge, they're not. And often they have some hidden symmetry, for example, chiral symmetry. And as a consequence, these states turn out to be extremely stable towards perturbations, especially thermal disorder or some sort of noisiness you add to the system in terms of impurities. All right, and that's of course also of technological interest, because if you can stabilize quantum states by endowing them with some topological features, then you can make them longer lived. And for example, for qubits, this is something highly desirable because often qubits decay before you can operate on them. So that's driving, I guess, motivation why people are interested in topological features. And I guess the open question, and that's the one we're focusing on, is usually when people investigate topological systems, they really stop at investigating what we call single particle states. So these are basically non-interacting systems, non-interacting Hamiltonians, which have these features. However, if you add interactions, it gets actually more interesting because the interactions cause non-trivial collective states, right? So for example, plasmons or Cooper pairs. And the question is whether these collective states also have topological features and topological protection. And that's the main question we want to address. Okay, so a quick outline. I'm going to just have a slide or two on the method that we're using. And then I'm going to discuss two paradigmatic examples, one in 1D and one in 2D. And I finish off with some engineering applications we're envisioning and which might be stimulating for discussion. All right, so that's it. So let's start with basically just first a high-level description of what plasma oscillations are. So they're basically collective excitations of electrons which arise from long-range Coulomb interactions between them. And these excitations, they're basically waves, electron density waves, which form a certain pattern in the bulk or even on the periphery of systems. Usually when you excite them with light, you shine light at them, that will cause these electron density waves, right? And they're quantized, and quantum of these oscillations is called plasmon. And as I mentioned before, they can be manipulated and used. Plasmons, not even in topologically trivial systems, can live on surfaces. They can be confined and intensified through the confinement, and you can use them in waveguides. So what we're doing here, since we're interested in edge phenomena, so things that happen at the boundary of systems, these systems are by definition not translationally invariant. You don't really consider periodic boundary conditions. So you have to do the treatment we're doing to obtain these collective states in real space. So usually when you learn about how to do the random phase approximation and obtain plasmons, it's sort of textbook physics, but you learn it in momentum space, and which is also helpful in terms of interpretation of dispersion curves and so on. However, that's not an option here. So we have to have a real space formulation. And so the central thing to calculate initially would be this polarization function. In order to calculate it, you have to have a Hamiltonian, in this case, a non-interacting Hamiltonian, of which you know the eigenenergies and the eigenstates. And when you do that, then you can construct this object that is a non-interacting polarization function. However, then what you do is you include the interactions on the RPA level. And in this case, these would be unscreened Coulomb interactions. In fact, you can add a screening term in front of the denominator to represent the environment, but that we'll do later. And anyhow, so from these two objects, the polarization function of the non-interacting function plus this interaction term, we can construct a matrix that will represent the dielectric response on the RPA level. And actually, we will find that all the features we're looking for, they do occur on the RPA level. So this is sufficient and easy enough to do for system sizes that allow about 1,000 or so atoms in any kind of arrangement. And then I guess in order to make connection with experiments, we analyze this dielectric function. For example, electron energy loss. Spectroscopy measures basically the poles in the inverse of this object. And these poles correspond to collective excitations, i.e. plasmons. And the corresponding eigenstates, they are basically these charge modulation states that we can also visualize. All right, that was enough in terms of formalism. Let's talk about some results. So we're going to first look at some paradigmatic model, which is called the SSH model, or in one dimension. And so it's basically a system that has a chain of atoms that are connected with each other by hopping integrals that alternate T and T prime, right? And we consider open systems, right? And it turns out, so you can write down a Hamiltonian that basically describes the alternating hopping T and T prime. And it turns out that the properties of these systems depend on whether T is larger than T prime or T smaller than T prime. And note that T is the outmost coupling between the first and the second, and then also between the next to last and last atom. So if T is smaller than T prime, then actually there's a weak link here compared to strong link here. And in that case, you get a topologically non-trivial regime. And if T is actually larger than T prime, it's trivial. And this is reflected immediately in the spectrum of single particle states. So here we order them by their magnitude. However, you can think of this index, this is done in real space obviously, but you can of this index as an effective momentum, right? So what we do see then is we see both in a trivial and non-trivial regime, a band here, a lower band and an upper band, and a band gap. And then only in the non-trivial regime, so only when T is smaller than T prime, do we also find these additional states in the gap. And these zero energy states in the gap, these are these topological edge states. So in order to confirm that, you have to actually plot the eigenfunctions that correspond to these states, and you find they're localized at the two edges, two edge points of the open chain. Right, so that's the non-interacting part. But now what you can do is you can calculate within RPA the dielectric function and analyze its poles. And in that case, you also see a difference between the trivial and non-trivial phase. So in both cases, you get a continuum of excitations, a lower one and an upper one. The lower one basically arises due to two particle excitations between bands, and then the upper one within band, single electron bands. And when you analyze the eigenstates of these continua, you find that their charge distribution is throughout the bulk of the system. So these are actually bulk excitations, right? And only in the topologically non-trivial phase, so when T is actually smaller than T prime, do we find in addition to that these states in the gap. And these states these are now not single particle states, these are plasmon states. They include interactions, so they actually depend on the strength of the interactions. And they're also localized like the single particle states at the edges of the system. So on that level, you can argue that if you look at single particle physics and you add Coulomb interactions, you get similar phenomenology. However, these edge modes, they are non-trivial many body states, and so they have properties that differ also from just being localized at the edges, like the single particle states. So let's go on and first confirm that these many-body states are actually topological in nature. And so what we can do is when we do the sum, we can actually separate out the edge contributions and the bulk contributions. So we just sort of turn the sum into two sums with a topological part and a bulk part, and then we can basically calculate instead of what we did before, calculating the full polarization function that use all contributions here. We can separate out the topological part, which I think is informative. So what you're looking at here is what we've seen before. If you do the full function in a trivial state, then you get this lower continuum and upper continuum of plasmon oscillations, which are bulk states. However, if you look only at the topological channel, then you get these interesting peak states, and they are localized on the edges, right? And so you can see that these edge states they come mainly from the single particle edge states. However, you see they're actually also influenced by the bulk states, single particle bulk states, because they're actually shifted, right? So the bulk states do affect, on some level, these localized plasmons, but they're still localized, right? But for example, affect them in terms of energy, and what we'll see later on, they also affect them in terms of stability, right? So it's not that the bulk, there's no scattering between bulk and surface states once you add the long-range Coulomb. There is scattering. So also what you can see is, if you're just doing this game, we're doing separating out the topological states, then we find the single electron states have some chirality. That's the blue line. And then you find that if you just consider topological contributions to the plasmons, they actually have the same chirality. However, that's the orange. However, if you include the contribution of the bulk states, in that case, you find actually that aspect is lost, right? So these actually collective modes inherit some but not all properties of the single particle parents, if you wish. All right, now let's do one more example where we take the same model, but we put an inversion mirror plane in the center, such that actually in the center we have an interface where a T is a neighbor of a T, whereas everywhere else a T is a neighbor of a T prime. And this will create a localized state here, in addition to possibly localized states here and here, right? So we have an interface localized state. And again, depending on whether T is larger or smaller than T prime, you might get this the state, only the state in the middle. So this is when you have a strong T, so T is larger than T prime, then you get one big single electron state in the center. On the other hand, if T is smaller than T prime, then you get linear combinations of edge states here, here, and here, and they are depicted here. So in one case, you get actually 3 zero energy states. In the other case, you get 1 zero energy states at a state at the interface. Now you can ask again what happens when we add Coulomb interactions, and as you can see, you have bulk phenomena that always exist, even in the trivial case, plus surface phenomena that depend on how you have tuned T versus T prime. So if T dominates and you only have that single electron state that's localized at the interface at the mirror plane, in that case you get one big plasmon mode localized there. And in the other case, you're going to get plasmon modes that have components at the interface as well as at the corners. So one thing that's different, though, is how these states actually are screened. So, for example, if you add some, I'm not showing this here, I just wanted to mention it. If you add some screening, this will be stronger affected by some screening substrate than these states. And the reason is that the contributing states that make up the state, they're all centered at the middle. So you are having basically a higher potential energy by forcing charges to be close to each other. And obviously in that case, if you put in some screening, that will reduce the Coulomb repulsion more drastically compared to the case where the electron charges are pretty far from each other in these states. Okay, so then let's look at what I find sort of the most interesting part is, so you can ask now how robust are these states, and we're going to focus on this central interface mode at the mirror plane. And so the robustness we will test by looking at the effects of what we call diagonal disorder. So our hoppings T and T prime are now taken from a random distribution that are still centered at the original T and T prime, but there's some randomness in them within some sort of range, negative A to A. So small randomness added to the hoppings. And then of course we have to do several realizations, like typically 500 in average over them. And so let me just, this is maybe too much, but so I'm going to just tell you the take-home message here. So this you probably know, this is the single particle density of states. So there are no interactions in figure A. And in that case, you see a lower band and an upper band, and you see the topological edge states in the middle. And now as you increase the disorder, you find that the topological edge states don't care at all about the disorder. This peak stays the same whether the disorder is small or large. However, the other states, they do actually decay with disorder. And so this is like a typical paradigm of topological protection versus topological decay of the trivial states. And these are obviously the non-trivial. Okay, so now you can ask what happens if we add interactions and look at collective states. And the answer is, well, so collective states, focusing on basically the interface state, it actually does decay. So what you find is it decays, and the reason is that this interface state is not only made up from the topological edge states of the single particle Hamiltonian, but it also admixes bulk states. But you find that it has both contributions, and so it's not fully protected, but it's kind of protected. So you can actually quantify how well this is protected by calculating something we call the inverse participation ratio. I'm not sure whether you guys know this stuff, but it's sort of in StatMech of random systems. Usually the first quantity people look at. It's not describing the full counting statistics, but I think it's a good measure. And what you find is if you focus on this state, it stays completely stable. So that would be, for example, a black line here. So as a function of disorder strength, the state doesn't change at all. And then what you find for here, for the many-body state, the plasmon, it actually does decay. However, it decays sort of slowly. It is decaying, we can fit it to e to the minus disorder strength squared divided by some constant. And so it sort of decays slowly. So it is kind of protected, if you wish, because it could decay much. So a bulk state would decay much more rapidly. If we separate out just the topological part like we did before, then that is actually completely protected, right? So the take-home message is that actually the collective excitations are less stable than the single electron states. And there is some delocalization going on. However, some of the protective aspects are still there because the decay with disorder is sort of less than you would have in a regular metal. Okay, so then let's do 2D. So this is the 2D version of the SSH model. And in this case, you don't only have a single chain with alternating hoppings, but you have these plaquettes. And in this case, I apologize, we use slightly different convention that's often used in the literature. So W and V are what we called T and T prime before. So these are hoppings, strong and weak. And so there are a few comments. So this is actually a generalization of the 1D system, and In the 1D system, the topological non-trivial nature is actually due to some symmetry protection that's sort of special, and this is carried over to this model. So this is not like other 2D topological insulators, but turns out that the collective excitations are actually the same as other topological insulators in 2D. So the system is special in the sense that it doesn't get characterized by a barrier curvature, but you have to look at some different topological invariant to characterize it, which is called the Zag phase. And that's inherited from 1D SSH model. And within that, you can say that there are trivial and non-trivial regimes, and they depend on the relative value of W and V, right? And so basically, if you have if these couplings on the surface are weak, you will get topological edge states, and it's going to be topologically non-trivial with basically a pi-pi Zag phase. And if it's the other way around and the V states are dominant, then in that case you don't have, I'm sorry, when the W states are dominant, then you don't have any edge states, and it's topologically trivial. Okay, so I'm not going to dwell on this, but this is basically the single particle spectrum. So again, no interactions on this slide. And then of course, the big question is what happens when we turn on interactions. And so basically what you're going to see in that case, again, is plasmons. And so let me just lead you through this by contrasting the plasmon spectrum of the trivial and non-trivial case. For the non-trivial case, there's no edge states, and in this case, you just have these the red states, which is a continuum of bulk states, right? However, and the bulk states, by the way, they look like this. Those are charge modulations that live in the bulk, right? So, and they're common for both the trivial and non-trivial phase. They live at higher energies, and so let's focus on the non-trivial case when you have edge states. In that case, you also get edge plasmons, and what you can see is actually they disperse. So you get this band of edge plasmons this here. And you can actually characterize it by the charge modulations and translate that into a K vector. And if you do that, then you find that they actually disperse like a one-dimensional system, right? So you have an effective one-dimensional system living on the periphery of the square, which is kind of cool, right? And there's this continuum of states. There's another special state here, which is that I haven't mentioned, but there are also corner topological modes. And they give rise to this peak. So this, how do you say, those edge states and those corner states, they only show up in a topologically non-trivial sector, and they should basically be the most visible aspect of a system like this if you shine light on it. All right, so I don't want to go all into these details, but and I've pretty much described the take-home stuff. So you find these two features only in the non-trivial phase. Let's just finish up by talking a little bit about engineering possibilities using such systems. And so what I have in mind here is to have an active area, which is like a 2D topological system, or maybe just a trivial system in this case, and some environment that I can use to manipulate what's the screening in the system. Right, so the environment would be some sort of dielectric substrate, and the active area would be some sort of metal. And what you see is, I mean, if you basically just put in one dielectric constant above and below this active area, you find there's a regime where the bulk modes in this case are highly susceptible to the dielectric constituent of that environment, whether it's 1 like vacuum or 9 like super large screened. And in that case, you find that the response is quite different in some energy range, which we call intermediate energy range, right? And we want to later on utilize this strong dependence in this energy range. Just to give you some ideas how the modes look in this energy range, we basically looked at 3 dielectric substrates and just a 2D metallic layer. And so for small dielectric environment, we get, let's say at some intermediate energy, we get this kind of dominant mode, and then at intermediate screening, we get something like this, and then at large screening, something like this. So you can see that just by putting it into an environment, you can get vastly different dominant modes. All right, so how can we make use of that? So for example, we can make waveguides, or we can make interfaces. So I guess the first step is, instead of one, we use two dielectric constants in two parts of the environment. And in that case, what you can do is, as a reference, actually the red line is a homogeneous case where the dielectric environment is basically vacuum. So that's the red line, and you see this here, it peaks at some energy range that's shaded in green, and then the other reference point is when the dielectric environment is very large screening. So in this case, it's flatter, and there's a little, I guess, a peak here that's not that's absent for vacuum. And then if you put them together, then of course you get some non-trivial stuff that you have to evaluate numerically, and you find you inherit some features from the not so much screened and for the highly screened system, right? Obviously, these are composite modes now. And so what's fun in this case is that you can actually utilize this to localize your plasmons either on one side or on another side of this sample, right? So for example, for low energies, you find it mostly localized on the right side. So in this case, where the environment is highly screened, and then at high energies is the opposite, and it's actually localized on the left side, where the environment is weakly screened or not screened at all. Right, so you can see how, without actually touching directly the active layer, you can play games by using different substrates. So my final result then is basically when we add yet another substrate, so we now can make waveguides, and we can aim to focus, let's say, these plasmonic modes in the center. And then this sort of demonstrates how this works. So I guess we use one a dielectric environment, another one, and then the first one again. And if we tune it, then we can actually localize plasmons in the middle layer. However, if you try to localize them too much, then you find that the contrast between inside and outside gets lost. Right? So there's sort of a trade-off between localizing these modes and between getting a sharp contrast between these various regimes. And so that's sort of the take home here. So let me summarize. So there's a bunch of publications we have recently put out on this. And so the three messages is that the topological character of single particle states is inherited by excitations, including plasmons, collective excitations. And we've shown some 1D and 2D examples. It was also shown that there's topological protection. That's the second point, but it's only partial for the collective modes versus basically perfect topological protections for the underlying single particle states of a non-interacting system. And so the last thing was sort of just a taste of what you can do with plasmons in 2D metallic layers by changing the environment and structuring the dielectric environment. Okay, with that, I would like to thank you for kindly listening, and I would be very happy to open it up. And I'm also happy I'm hopefully within the 45-minute, 30-minute boundaries.
Great. Thank you so much, Stephen. So this is excellent. Let me thank everybody who is here, and also Stephen, for this very nice talk. We have a lot of questions for you. So Satwik, you can go ahead and stop the streaming, and we'll get started with our next.